Hey everybody, welcome back for a third installment of Periodic Trends. Yes, this is not Periodic Trends Explained, but Periodic Trends Explained Further. Yes, the third video. Bear with me, I know that this is a lot, but I really want to make sure that you guys get this part. So, actually the first two videos should be enough, but if you need the third video, it's here, and I'm really going to do is I'm going to try to go through all the trends that we talked about and apply what we did in that last video. In the last video I talked about the effective nuclear charge and essentially how the effective nuclear charge changes as we move through the periodic table. Okay, and we'll go through more in class and talk about examples in class, but that's essentially the idea. So what I want to do now is I just want to go through all of these trends and just kind of quickly explain using that idea. So let's start right away with atomic radius. So we saw when we looked at atomic radius that the atomic radius decreased as we went to the top right. Now, why is that? Well, as we move to the top right of the table, what's happening is we move to the right. Let's start with that. As we go from left to right on the periodic table, we're adding elements to the same energy level. So therefore, shielding does not change overall from left to right. Yes, there are some dips that we see. So when we go from the S to the P, there is that little bit of dip in atomic radius because of the S's can be shielded. But overall, the effective nuclear charge increases as we go from left to right because the shielding does not increase at all. Now when I go down from hydrogen to lithium to sodium to potassium, what happens is I add a new energy level each time I go down. So as I go down a group or family, increasing energy level makes the atom get bigger and bigger and bigger. Think about it. If the nucleus is the only thing pulling on the atom, right? Pulling on the electron, then what we should see happen is we should just see the atom get bigger and bigger and bigger, because as you add more, we should see it get smaller and smaller and smaller, because as you add more protons, it should get stronger and stronger at pulling electrons. But that's not the case. Hydrogen is not the biggest element, and element 118 is not the smallest one. Okay, that's because we have energy levels, orbitals, S's, P's, sublevels, because we have quantum mechanics. This is evidence further that quantum mechanics works. Alright, so as I go down, I add an energy level, therefore it reduces the effective nuclear charge. Effective nuclear charge goes down, so Z, E, F, F goes down. Shielding is going up as I add a new energy level. And these are the things you want to say. So if they ask you, why is cesium bigger than lithium? Well, because cesium has a lot more electrons in higher energy levels, further away from the nucleus, and has a lot of shielding. Shielding has gone up, and the effective nuclear charge goes down, so therefore the electron can get further and further away. That's how you explain that. Do not say that cesium's bigger because it's at the bottom of the periodic table. That is not the answer. A lot of students do that. So many students say that the AP test has complained over and over and over again. This is one area you can actually squeak out some real good points, guys, really. Okay, so that's atomic radius. Okay, as I go from here, effective nuclear charge increases without a change in shielding overall. Okay, again, we can look at all the little anomalies as we move. All right, then we talk about ionization energy. Okay, same thing we talked about before. If I go from hydrogen to helium, there's an increase in ionization energy. Why? Because effective nuclear charge went up. The effective nuclear charge goes up because there's more protons, there's no shielding, and therefore the nucleus is better at pulling the electrons, hence helium will not let go of those valence electrons. If I go from hydrogen notice it's way down here in a lower energy, so hydrogen can easily lose that electron, okay, compared to helium. So we drop from helium to lithium, going down, right, going from hydrogen, let's do it this way, hydrogen to lithium to sodium to potassium, going down a group or family. If I go down a group or family, the ionization energy steadily goes down, okay, because we're adding a new energy level. So we have an S2S, a 3S, a 4S, a 5S, a 6S, and a 7S electrons, right? So as I go from top, which is hydrogen, 1S to 2S, I add a new energy level, so therefore the effective nuclear charge is going down. Why? Because shielding is going up, okay? Now, if I go from lithium to neon, I'm going across a period on the periodic table. Well, lithium is going to be the smallest smallest ionization energy, while neon is the highest. Again, just like hydrogen to helium. I add the electrons, shielding overall stays the same, but here's two anomalies here and here we talked about before. As I go from beryllium to boron, what I'm doing is I'm adding an S to a P. So that's where I go from the 2S 2s2 from a 2s2 to a 2s 2p1. I added in a new sublevel. Since I added a new sublevel, I'm increasing the shielding and therefore causing the effective nuclear charge to go down. Therefore, ionization energy will be a little bit weaker, right? We don't have to add as much energy. Remember, ionization energy is energy added. So I'm not going to have to add as much energy because this 2p electron is shielded by that 2s. So you can have shielding within sublevels as well as between, between energy levels. So energy level change, sublevel change. Then when I go from here, which is the, what I called that was the 2, oops, let me try that again. The 2s3 to the 2s4. Oh, shoot, let's try that again. 2p3, because that didn't make any sense. 2p4, there can't have an s that high. Okay, because what I'm doing is I'm adding that electron and doubling it, right? I'm starting to double up. So 1, 2, 3. 2p3. 2p4, I add the extra electron, and then we get that repulsion. And this is that one place where that repulsion can come into play for ionization energy. So ionization energy again decreases because the repulsion force overcomes the effective nuclear charge, making it weaker, therefore lower energy required to knock that electron out. And then the pattern continues. And that's how you explain ionization energy. All right. Multiple ionization energies. When we're talking about the multiple ionization energies, I kind of already laid this out for you, right? So we already talked about the fact that if we have sodium, which had that 3s electron, and that's the first ionization energy that hits it, 496, well, because it has shielding. If I lose this energy level, because that electron is now gone, and now I have sodium plus 1, and I try to take out a second electron, well, shielding has dramatically gone down. Since shielding has dramatically gone down, this electron is going to be a lot harder to remove, hence why ionization energy dramatically goes up. And we keep seeing this. Now this was magnesium, right? And magnesium had the 2 valence electrons, and that was the first and the second. Again, easier to remove. And here's a question for you. Why is the second ionization energy almost double that of the first ionization energy? Well, if we look at those 2 electrons, they're in the same energy level, so you can't say shielding is any different. They're both in the s, right? These are both a 3s2 electron, so you can't say the p is shielding. This is going to be repulsion. Repulsion is going to explain this. Because I have 2 electrons in here, they're pushing away from each other, right? These electrons are trying to get away from each other, but they're in the same orbital, okay? Since they're pushing on each other, that first electron has a little bit of a push from its buddy, right? This electron here kind of repels it and gives it a little bit of an oomph, kind of, it's a weird sound effect, I'm sorry about that, pushes the electron out, okay? So therefore, this requires less energy. This electron's gone, you've got this electron left behind, well there's no other electron giving that extra push, and therefore actually feels more of a pull from the nucleus, and therefore effective nuclear charge goes up. Okay, and then once that electron's gone, we're then hitting this with a, going into those inner core electrons now for E energy level, ionization energy 3. So that third electron is where we now have shielding is dramatically gone. We now have a reduced in shielding, therefore an increase in effective nuclear charge, a lot harder to get. And I think you can apply that for all the other elements. All right, effective nuclear charge, electronegativity, a lot of E's in this chapter, so be careful. Again, as we go from left to right, I think you should be able to explain this. Same thing we saw before. Why? Because the effective nuclear charge is increasing, therefore fluorine is better and better at pulling the electrons, okay? And cesium is not. I don't think I need to explain this one, but if you want me to, I will in class. This is pretty much the same as atomic radius, just transfer over atomic radius with electronegativity. Electron affinity, the same idea. Okay, so we're going to have some problems. There's some things that pop up. So if we look at this, fluorine's really good because it still has an empty spot, can fill it in, and then go to neon. Now, why are the noble gases positive? Remember, electron affinity is the energy released when an electron is added to the atom. All right, so this means energy. If I want the helium or neon or argon to gain an electron, I have to add energy to do that. And that's not what we want. If I add an electron to fluorine, boom, heat comes out, energy comes out. It happens all on its own. Here I have to force it in because the energy level is complete. In order to do the, go further, I'd have to add a new energy level, and that's not going to be possible. Okay, so there's your explanation why that's positive. For over here, the S's are filled. The S's are filled. We have to add that P to get from beryllium to boron. And again, that's going to require energy to do so. Okay, so we tend to see that, beryllium, magnesium, they're never really going to gain electrons. These can, but again, it depends on what they're bonded with. Okay, and I'm going to finish this up with explaining the atomic radius. Atomic radius is due to the fact that if I have lithium and it has that 1s2, 2s1 electron, well, if it goes to the lithium plus ion, right, the lithium ion, it's 1s2. It lost this energy level. Since the energy level is gone, the atom gets smaller, right? You've got n equals 1, n equals 2. Well, if this electron's gone, the energy level's gone. What happens to the size of the atom? It gets smaller. Okay, and that's it. It's all you have to say for formation of cations, is the loss of an energy level. Effective nuclear charge goes up, shielding goes down, and the atom gets smaller when it forms the ion. Okay? All right, and the last part, which is the formation of an anion. Why does this get bigger? Well, if we look at something like fluorine, fluorine is a 1s2, 2s2, 2p5. Well, the fluoride ion is a 1s2, 2s2, 2p6. So what we're doing is we're taking that p orbital and we are filling up that last electron into that orbital, right? So what's happening is, if I put an electron here, now let's take a look. Did the energy level go up? No. So did shielding change? No. Shielding stayed the same because we're in the same energy level. Did I add an S or a P? No, that stayed the same. So I can't say that shielding is changing due to the increasing of an S or a P. So that stays the same. Did I increase the protons? Did the protons go up? No, protons stayed the same. It's still fluorine. Fluorine is fluorine. So the effective nuclear charge really can't go up because it didn't increase the protons. So what is the only thing possible left is electron repulsion. And this is the third place that electron repulsion has an effect. Because we're adding an electron to the same energy level, same sublevel, same number of protons. They repel each other, causes the ion to increase in size. Okay, and that's it. That's your explanation of all the periodic trends. And we'll go into more detail in class, but hopefully this, I know it's long and I apologize, but hopefully it covered everything for you. Talk to you later, guys.